All right, so welcome Algebra 2. We are jumping into lesson 72, and you can find that on page 301. So it's first starts out with lines from experimental data. So you can tell looking at example 72.1 and the picture there that they're just taking the data and then plotting it and seeing what kind of information that yields. So it says write an equation that expresses salt as a function of carbon. So they're showing how there's different lines that can be drawn. So anytime that you have data like that, you have to just draw what is called the best fit data. Now, a lot of scientific calculators now, you can actually plug in the different points of data and it will find the average of all of that, and you can plug it all in. So I would encourage you to look up YouTube videos about how to plug in that experimental data into those graphing calculators. They're a lot more advanced than when I was in school. So I'm really impressed with all their capabilities and what they're able to do. All right. One thing I want to point out to you is on page 302, it's in boldface, so I'm going to read it to you. It says, your answers to problems like these in the problem set should be approximately the same as the answers given in the back of the book. Boldface. However, they will almost never be exactly the same as the answers given in the back of the book. So here's the reason is when we look at the data, we're just trying to find the best fit. And if our data, let's say that I have maybe a graph and I find the trend in my data looks like this. Well, I can tell from the trend in my data that my data is going upward, right? It's a positive slope. But if I asked each of you guys, hey, I'd like you to graph and give me an equation of a line for the best fit data. Well, each of you guys are going to try to, we don't want to put a line that's like here and say, well, that's the best fit data. Well, that wouldn't be true because there's way more data below it than above it. So that would not be the best fit. But each of you guys may have it just a little bit off from the other, but I'm sure that your slopes would be similar, just not necessarily precise with each other, because you're just taking the data and you're trying to find where is it most likely an average of all the data that's given. So that's where we get the best fit line. And there is a place in graphing calculators now that you can actually plug in the different pieces of data and then find the best fit line, technologically, not just eyeballing it and saying, well, it looks like the slope is approximately up 6 over 4, or whatever. But I would encourage you when you're doing problems like this, grab some graph paper. I hope you guys have some graph paper at home. I love graph paper. I just love the mechanics of it, how it's all organized. So I think graph paper is a great help. If on this, you can see I'm kind of sketching it, so my line could be crooked or whatever. So on graph paper, I would ensure that it was precise. Each box is the equal distance apart, so it's just a lot more likely to come out correctly. All right, if you look at the bottom of page 302, it talks about negative angles. So a negative angle, we've dealt before with positive angles, but negative obviously is going to go backwards the distance that we typically do. So normally we start on the x-axis and go upward. That's positive. So the book is showing you on page 303 that when it's negative, you're going to start still at the x-axis, but you're going to go down into quadrant 4 instead of across quadrant 1 like you had been doing. So again, look on page 303 and kind of take a look there. So they're showing you that angle that is formed 36.87 degrees is the same thing as negative 323.13. And how did they come up with that? Well, they went, backwards. 180 would be half, and then another 90, and then finding that distance there. So we can see that on page 303. Now, the bottom example on page 303 talks about example 72.2. It says write, and what we're doing, we're taking our polar coordinates and writing it in rectangular coordinates. So we know that 4 is the distance of the line. And then it says negative 210. Well, I know that every straight line is 180 degrees. So if it's 180 degrees, then I can take 210 and subtract 180, and that's going to give me 30 degrees. So notice in boldface it says solution. We're on page 303. The solution there, it says, we always measure the angle first and then measure the length. Then we draw the triangle. So how do we solve what A would be? So that they're showing you now we solve for A and B based on that. So then remember that rectangular coordinates are right or left and then up or down. So that's how they were able to solve that. So you have to figure out how far you went. Right would be a negative number because it's in quadrant 2. And then it went up 2. So that's how we can figure out how to write it. All right, let's take a look at page 304, and we're looking at practice A. All right, so we kind of talked about the best fit line and the data, but let's take a look now on page 304, and it's practice A. And I'm sorry, I'm having to erase my board so that we can take a look at that first practice problem there. All right, so practice A says it is 5, so the line would be 5, the radius, and then the angle is negative 230 degrees. All right, so that is practice A. So what would that look like? Well, if it's negative 230, then let's take a look at my XY axis. So since it's negative, I'm going to come downward instead of typically we go upward, right? Well, I know 180 would be the first. So if it's 230 minus 180, that leaves me with 50 degrees, right? So if I have 50 degrees, then it's going to come up this direction. And this would be 50 degrees. And I know that this is 5, right? So I solved all of that based on what they gave me here. The length of that radius there is 5. And then I did 180 minus 230, and that gave me 50. All right? So that's how I've got it so far, and I know that's 5. Now, I've got to find this distance. So I've got to find A and B. It might help if I did it a different color, wouldn't it? Let me grab my black so that way you guys can see exactly what I'm looking for. I'm looking for A and I'm looking for B, right? So I drew my picture there and I'm looking for A and I'm looking for B. All right, so since I'm looking for A, and so the sine of 50 degrees equals A over 5. All right, so if I'm standing here, the sine would be opposite over hypotenuse. So A would be, if I put this as a ratio and cross multiply, 1A equals, or just A, equals 5 times the sine of 50 degrees. And I want to point out to you, make sure you're being careful. You can type on your calculator sine of 50 times 5, but be careful. When you press sine, a parentheses usually pops up. Make sure you end that parentheses because you're only doing the sine of 50, not 50 times 5. You're not finding the sine of the whole thing, just the sine of 50. And sometimes I'll just type that in my calculator. Sine of 50 equals, and press enter, and then times 5. Or you can press 5 times the sine of 50. But be very careful if you do sine of 50 first that you end parentheses before you multiply times 5. I hope that helps. So when I type that into my calculator, I should end up with A, notice a wavy because I've got to round to the nearest hundredth. So A is approximately 3.83. All right. So I found that out based on the polar coordinates they gave me. I'm looking for rectangular coordinates, right? So I know now that A is 3.83 equals A. Now I've got to find B. Remember that it's right or left first, then up or down. So now